Oracle Database Management System. Background processes. Oracle's DBMS employs several background processes to manage the database efficiently. Key processes include SMON. System Monitor performs crash recovery, checks database consistency, and cleans up temporary segments. PMON, Process Monitor, detects and recovers from the failure of child processes. DBWR, Database Writer writes modified data from the buffer cache to the data files on disk. LGWR, Log Writer writes the contents of the redo log buffer to the online redo log files on disk. CKPT, Checkpoint creates fixed points in time during database operations, recording the current state of the database for recovery purposes. Performance and fault tolerance. The redo log and buffer cache in Oracle are mechanisms designed to enhance database performance and ensure data durability and consistency. The redo log records all changes made to the database, allowing recovery from failures. The buffer cache stores recently used data in memory, enabling quick access to frequently accessed data. These mechanisms are akin to the principles of MapReduce, where data is split and processed efficiently to improve performance and scalability. Data models in databases. Data models in databases. Conceptual, logical, and physical models. In databases, data models are structured in a hierarchy. Conceptual model describes real-world entities and relationships represented by the data. Logical model describes how the data will be organized and stored, considering data types, relationships, and access requirements. Physical model describes how the data will be physically stored in the database, using specific structures like tables and files. Types of models. Physical model often employs hierarchical and relational models. Logical model typically uses object-oriented models or entity relationship (ER) models. The choice of model depends on the organization's specific requirements and preferences, with some opting for a hybrid approach combining elements of multiple models. Integration of process and data models. In the context of business or enterprise architecture, process models and data models serve different but complementary purposes. Process model describes the flow and interaction of activities within a business process, showing the order of activities, inputs, outputs, and relationships. Data model describes the structure and organization of data within a system, defining entities and their relationships. Together, these models provide a comprehensive understanding of how a business process functions. The data model defines the data used and generated within the process, while the process model defines how the data is transformed and used by the activities. Understanding query languages, SQL, and beyond. Introduction. Query languages are essential tools for managing and manipulating data within databases. Structured Query Language, SQL, is the most widely used query language for relational databases, but there are several other query languages tailored for different types of databases and purposes. This essay explores SQL, its variants, and other non-SQL query languages, highlighting their unique features and applications. Additionally, it delves into the relationship between SQL, relational algebra, and query by example, QB, and outlines the process of query execution in databases. SQL and its variants. SQL, the standard query language. SQL, structured query language, is a standard language used to query and manipulate data in relational databases. It is a declarative language that allows users to retrieve, update, and manage data stored in tables. Common SQL commands include select, insert, update, delete, and join, which facilitate a wide range of database operations. Variants of SQL. SQL has several variants, such as ANSI SQL and Oracle SQL, which add additional features and syntax specific to different database systems. These variations provide enhancements and optimizations tailored to the specific capabilities and requirements of the database management systems, DBMS, they support. Non-SQL query languages. Introduction to non-SQL query languages. While SQL is the predominant query language for relational databases, there are numerous non-SQL query languages designed for different types of databases, such as NoSQL databases. These languages cater to the specific needs of their respective database systems, offering unique features and syntax. Examples of non-SQL query languages. 1. MongoDB Query Language. MQL used for querying and manipulating data in MongoDB, a NoSQL document database. 2. Cassandra Query Language. CQL designed for Apache Cassandra, a distributed NoSQL database. 3. Apache Tinkerpop Gremlin Query Language. GQL, a query language for graph databases. 4. Apache Drill Query Language. DQL used for analyzing and querying data across various data sources, such as Hive, MySQL, and S3. 5. Apache Solr Query Syntax, employed for searching and analyzing data stored in Apache Solr, a search platform. Learning non-SQL query languages. For those already familiar with SQL and programming languages like Python, picking up non-SQL query languages can be relatively straightforward. Many non-SQL query languages use similar concepts and syntax, such as select statements and where clauses, making the transition easier. However, it's essential to familiarize oneself with the specific syntax, commands, and features unique to each language. Relationship between SQL, relational algebra, and QB. SQL and relational algebra. Relational algebra is a formal system for manipulating relations, tables, in a relational database. It uses a set of operations, such as projection, selection, and join, to query and manipulate data. SQL incorporates elements of relational algebra, using similar operators and syntax to perform these operations. SQL and query by example, QB. QB Query by example is a query language that allows users to specify their queries by providing examples of the desired results. While SQL is more widely used, QB offers a more visual and user-friendly approach to querying databases. SQL can be seen as a practical implementation of both relational algebra and QB, providing a comprehensive language for querying and manipulating data in relational databases. Query execution process. Overview of the query execution process. The process of executing a query in a database involves several stages, transforming the query from its initial form to the final output. The stages include parsing, translation, optimization, execution planning, and evaluation. Stages of query execution. 1. Query input. The user inputs a query. 2. Parser. The query is parsed into its constituent parts, and syntax errors are checked. 3. Translator. The parsed query is transformed into a relational algebra expression or another abstract form. 4. Optimizer. The relational algebra expression is optimized to determine the most efficient way to execute the query. 5. Execution plan. An execution plan is created, specifying the exact steps to evaluate the query. 6. Evaluation engine. The evaluation engine executes the steps in the execution plan and produces the query output. Understanding programming models and database systems. Introduction. In the realm of data processing and database management, various programming models and systems are employed to handle and manipulate data efficiently. This essay explores the roles of different components within database systems, the distinction between high-level frameworks like Hadoop and Apache Spark, and the various database management systems, DBMS, used in the industry. Programming models in database systems. Programming models in database systems. The input-output flow in databases. In a database system, the input-output flow encompasses several stages, each with specific components responsible for processing and transforming queries. Key components include the parser, translator, optimizer, execution plan, and evaluation engine. 1. Parser. interprets the SQL query and checks for syntax errors. 2. Translator converts the parsed query into a more abstract representation, such as a relational algebra expression. 3. Optimizer determines the most efficient way to execute the query. 4. Execution plan specifies the exact steps to evaluate the query. 5. Evaluation engine executes the steps in the execution plan and produces the query output. These components form a programming model that processes a database query from its initial human-readable form to the final output. High-level frameworks: Hadoop and Apache Spark. Hadoop and Apache Spark overview. Hadoop and Apache Spark are high-level frameworks designed for processing large datasets in a distributed computing environment. They utilize the MapReduce programming model, which involves two main stages: a map stage and a reduce stage. 1. Hadoop, a platform for storing and processing large datasets using the MapReduce model. It is used for big data analytics, data warehousing, and complex data processing tasks. 2. Apache Spark, a fast and general engine for large-scale data processing. It supports batch and streaming data, machine learning, graph processing, and real-time analytics. Relationship to database systems. The parser and translator components discussed earlier are low-level components within a database system's processing pipeline. They are not directly related to Hadoop or Apache Spark, but are part of the underlying infrastructure of the DBMS. Database Management Systems, DBMS. Role and examples of DBMS. A DBMS is responsible for managing and processing data stored in a database. It handles queries, data modification, and other operations, providing a range of features such as support for SQL, ACID transactions, security, and scaling. Examples of popular DBMS include: 1. Oracle Database. 2. Microsoft SQL Server. 3. MySQL. 4. MongoDB. 5. Apache Cassandra. 6. Google Cloud SQL. These systems are suitable for various business sizes and applications, from small startups to large enterprises. Differences between small-scale solutions and large-scale frameworks. While DBMS like Oracle Database and Microsoft SQL Server are used by organizations of all sizes, Hadoop and Apache Spark are primarily employed by large organizations that deal with extensive datasets and require advanced analytics capabilities. Who uses Hadoop and Apache Spark? Use cases and applications. Hadoop and Apache Spark are used by organizations that need to process vast amounts of data quickly and efficiently. They are ideal for big data analytics, data warehousing, machine learning, graph processing, and real-time analytics. 1. Large enterprises, companies with significant data volumes and complex data processing needs. 2. Data-driven industries, sectors such as finance, healthcare, retail, and technology that rely on data analytics for decision-making and innovation. Optimization techniques and overview. Introduction. Optimization techniques are essential in various fields to find the best solution to complex problems. These techniques range from heuristic methods to more advanced approaches like mega-heuristics, swarm optimization, trajectory optimization, and evolutionary algorithms. This essay explores these different approaches, their applications, and the unique characteristics that make them suitable for various optimization problems. Heuristic techniques. Definition and application. Heuristic techniques are algorithms that use educated guesses or rules of thumb to find good solutions quickly. They are particularly useful when exact solutions are too difficult or time-consuming to compute. These methods are often employed at a lower level to provide approximate solutions efficiently. Examples. 1. Hill climbing starts with an initial solution and iteratively improves it by making small changes until a local optimum is found. 2. Simulated annealing. Inspired by the annealing process in metallurgy, It uses random perturbations to escape local optima and find globally optimal solutions. 3. Taboo search. Utilizes a memory structure called the taboo list to prevent cycling and help the algorithm escape local optima. Mega-heuristic techniques. Definition and application. Mega-heuristics are higher-level algorithms that utilize heuristic methods to tackle complex optimization problems. These techniques involve using local search methods, such as simulated annealing or taboo search, to iteratively improve solutions by making small changes. Characteristics. Higher-level approach. Mega-heuristics operate at a higher level, orchestrating multiple heuristics to solve more complex problems. Local search techniques. They often incorporate local search strategies to refine solutions iteratively. Swarm optimization. Definition and inspiration. Swarm optimization algorithms are inspired by the collective behavior of swarms in nature, such as flocks of birds or colonies of ants. These algorithms use a population of candidate solutions, agents, that interact and cooperate to find an optimal solution. Examples. 1. Particle swarm optimization, PSO inspired by bird flocking behavior. It uses particles that move through the search space, influenced by their own best position and the best positions of their neighbors. 2. Artificial bee colony, ABC based on the foraging behavior of honeybees. It mimics their method of finding and exploiting food sources. 3. Firefly algorithm, uses the bioluminescent behavior of fireflies, where light intensity functions attract fireflies to brighter sources. 4. Cuckoo search, inspired by the breeding behavior of cuckoo birds. It utilizes the strategy of laying eggs in the nests of other birds. Trajectory optimization. Definition and application. Trajectory optimization focuses on optimizing the path of an object moving within a dynamic environment under certain constraints. It is used in various fields, including robotics, aerospace, and animation, to ensure efficient and feasible trajectories. Evolutionary algorithms. Definition and inspiration. Evolutionary algorithms draw inspiration from natural selection and evolution. They use a population of candidate solutions and apply genetic operators like selection, crossover, and mutation to evolve better solutions over time. Examples. 1. Genetic algorithm. GA uses principles of natural selection to evolve a population of candidate solutions. 2. Genetic programming. GP evolves computer programs to solve specific problems or perform tasks. 3. Differential evolution. DE utilizes a differential mutation operation to generate new solutions from a population of candidates. 4. Harmony search. Inspired by musical instrument tuning processes, it solves optimization problems by mimicking the creation of harmonious music. Choosing the right optimization technique. Factors to consider. The effectiveness of an optimization technique depends on the specific characteristics of the problem being solved. Key factors include problem type. Different techniques are suited to different types of problems, whether continuous or discrete. Solution quality versus computation time. Some methods provide faster results but may be less optimal, while others take longer but yield better solutions. Hybrid approaches. In many cases, combining multiple optimization methods can be effective. Hybrid approaches leverage the strengths of various techniques to achieve a more comprehensive and optimal solution. Optimization methods. Linear versus nonlinear. Introduction. Optimization is a fundamental aspect of many real-world applications, involving the process of finding the best solution to a problem from a set of feasible solutions. Optimization methods can be broadly categorized into linear and nonlinear optimization. This essay explores these two classes of optimization, their techniques, applications, and the differences between them. Linear optimization. Definition and techniques. Linear optimization also known as linear programming, involves optimizing a linear objective function subject to a set of linear equations and inequalities. Linear optimization problems are characterized by their simplicity and well-defined solutions, making them easier to solve compared to nonlinear problems. Common techniques. 1. Simplex method, an iterative procedure used to solve linear programming problems. 2. Duality theorem, establishes a relationship between the primal and dual problems, allowing for efficient solution finding. 3. Sensitivity duality lemma. SDL analyzes the sensitivity of solutions to changes in parameters, aiding in efficiently computing the range of values for an optimal solution. Applications. Linear optimization is widely used in various fields, including supply chain management, optimizing logistics and resource allocation, production planning, determining optimal production schedules and inventory levels, control theory, designing systems that maintain desired outputs, financial management, portfolio optimization and risk assessment, nonlinear optimization, definition and techniques. Nonlinear optimization involves optimizing an objective function that is not linear, which often includes multiple local optima and more complex relationships between variables. These problems require more sophisticated techniques and are generally more computationally intensive. Common techniques. 1. Gradient descent, an iterative method that uses the gradient of the objective function to find the minimum or maximum. 2. Newton's method, an iterative approach that uses second-order derivatives to find optima more rapidly than gradient descent. 3. Quadratic programming, solves problems where the objective function is quadratic and constraints are linear. Applications. Nonlinear optimization is essential in fields where problems cannot be simplified to linear relationships, such as machine learning, training algorithms and models to minimize error functions, image processing, enhancing or reconstructing images based on complex criteria, optimization of complex systems, dealing with multiple local optima in engineering and economic systems, comparison, linear versus nonlinear optimization, efficiency and complexity. Linear optimization, generally more efficient, with solutions found using well-established algorithms like the simplex method. Problems are easier to solve due to fewer equations and well-defined solutions. Nonlinear optimization, more complex and computationally intensive, often requiring iterative and numerical methods. Suitable for problems that cannot be represented as linear equations and involve complex objectives or constraints. Concurrency control and transaction management. Definition and importance. Concurrency control is crucial in systems where multiple users or processes access and modify data simultaneously. It involves a set of techniques and algorithms to ensure data consistency and integrity. Key aspect. Transaction management groups a set of read and write operations into a single atomic action. If any part of the transaction fails, the entire transaction is rolled back, ensuring that the data remains consistent. Database systems, operations, concurrency control, and storage solutions. In modern database systems, efficient data management is crucial for ensuring consistency, reliability, and performance. This essay delves into the various aspects of database operations, concurrency control mechanisms, and different storage solutions, including their applications and benefits. Database operations. Read and write. Read operations. A read operation in a database system retrieves data, typically executed through SQL statements like select. For example, a query like select asterisk from users where age 30 fetches all user records with an age greater than 30. These operations are fundamental for accessing the stored information without altering it. Write operations. Write operations modify the data within the database, including insert, update, and delete statements. These operations are crucial for maintaining and updating the database's content, such as adding new records, changing existing data, or removing obsolete information. Concurrency control. Importance of concurrency control. In dynamic database systems, where multiple users or processes simultaneously access and modify data, concurrency control mechanisms are essential. These mechanisms ensure data consistency, prevent conflicts, and maintain integrity even during concurrent access. Methods of concurrency control. 1. Locking. This technique restricts data access by locking resources for a specific period. It prevents multiple users from modifying the same data simultaneously. 2. Timestamping. Transactions are assigned timestamps to manage the order of operations and check for conflicts before committing. 3. Optimistic concurrency. Assumes minimal conflicts, checking for consistency only before transaction commit. 4. Multi-version concurrency control. MVCC allows multiple versions of a data item to exist simultaneously, enabling concurrent transactions to access different versions without interference. Logging and log management. Importance of logging. In dynamic database systems, extensive logging records every significant event, such as transaction commits or rollbacks. Logs are vital for debugging, performance tuning, and auditing. Log management. To manage the large volume of logs, systems often use a log cache to temporarily store logs before transferring them to persistent storage. This reduces latency and improves performance by minimizing direct storage interactions. Storage solutions. File storage. File storage uses a file system interface where data is organized into folders and files. It is commonly accessed through traditional file systems. Object storage. Object storage, accessed via a RESTful API, stores data as discrete objects with associated metadata. It is ideal for scalable cloud storage solutions, offering flexibility in data management. Block storage. Block storage divides data into fixed-size blocks, typically used for databases, application data, and operating system files. It allows for efficient, low-latency access, making it suitable for high-performance applications. Distributed File Systems, HDFS. Overview of HDFS. Hadoop Distributed File System, HDFS, is designed for large-scale data storage and processing across multiple nodes. It uses a block-based architecture, ensuring fault tolerance and scalability. Role of name node and data nodes. Name node manages metadata, including file locations, ownership, and permissions. Data nodes store actual data blocks and handle storage capacity. Horizontal partitioning and sharding. Horizontal partitioning. Also known as table partitioning, this technique divides a large table into smaller, more manageable pieces based on specific criteria. It enhances query performance by reducing the data volume that needs to be searched. Sharding. Sharding distributes data across multiple database instances to ensure scalability and manageability. It is particularly useful for large datasets, improving performance and reliability. HDFS and MapReduce. Relationship between HDFS and MapReduce. HDFS provides the storage layer for the MapReduce programming model, which processes large datasets in parallel across a distributed environment. While MapReduce handles data processing, HDFS manages data storage and retrieval. Tools for partitioning and sharding with HDFS. 1. Apache HBase, a NoSQL database on top of HDFS, supporting sharding and partitioning. 2. Apache Spark, an engine for large-scale data processing with built-in support for partitioning. 3. YRN, a resource management layer in the Hadoop ecosystem that facilitates data distribution and partitioning. Database systems. Application independence. Concept of application independence. Database systems provide a structured way to store, retrieve, and manage data, allowing applications to access data without managing low-level storage details. This separation, known as data abstraction, enables multiple applications to use the same database system for various purposes.